So thanks for coming. So this talk about some architectural considerations for algorithms in Python. I will not pretend to have the solution for everything and the rest. So this talk is mainly propositions, ideas, and it's open for suggestions, questions, discussion. And it's mainly the goal of this talk is precisely to talk about this and share ideas about these kind of things. So first I will present a base scenario with some algorithm and a sub-algorithm. Secondly, I will show the problems with our initial implementation. Thirdly, I will show an architecture that's inspired from Scikit-learn. Then I will present a variant of this architecture. The fifth section will be about properties. So I think that most of you know properties, but I will show how to use them in general. And in the last section, I will use properties in our architecture to reach the final version of this architecture. And in conclusion, I will show quickly a simplified real example because we will work on the toy example for the main part of the presentation. So at last, I will show a more realistic example. Okay, so let's start with our base scenario. So let's say that you have a little algorithm that you want to use as a sub-algorithm in a big algorithm, okay? So here our little algorithm will be simply a dichotomy. So you input a function f and you output the zero of this function, which is supposed to be increasing from 0, 1 to r. So whatever the exact code, but what is important is the signature of the function. Here's just an example. I define some increasing function, and when I apply find zero dichotomy to that function, it outputs the value of the zero. Okay? Then we are going to pretend that we have a big algorithm, and in my case, the big algorithm will be really stupid. The big algorithm, you take the zero of the function, and you simply add a number. Okay? So in input, you take the function f, the amount of translation that you want. First, you find the zero by a dichotomy, and then you add a number. Okay? So, of course, in a real example, it will be costly calculation and more complicated stuff. But essentially, you have a big algorithm that relies on a small algorithm. And here is just an example of application of this big algorithm. Of course, it will be interesting to be able to vary the sub-algorithm when we use the big algorithm. So we can imagine that we have another function, another sub-algorithm that also takes a function as an input and that outputs a number. In that case, for example, it inputs a function and it returns the argmin of the function with a golden section search, but whatever. And okay, so here's just an example. We applied the find argmin algorithm to a function f, and it outputs something, a number. Okay, so now if I want to be able to do this, I will need to modify a bit the big algorithm so that it takes the sub-algorithm as an input. So now I will also take as an input the kind of sub-algorithm that I use. And here, of course, I'm modifying the line in order to use find point instead of find dichotomy always. Okay? It's clear for the moment? Okay, so now I also input that and have the result. Okay, so that was the naive implementation of our architecture. But we are going to see that there are several problems with this implementation that will prevent us from going forward with the code. So, first problem. Imagine that you want to enrich the input of your sub-algorithm. So I don't know if you noticed, but for the moment in the dichotomy, for example, I used a precision of 10 to the exponent minus 6. And of course, that could be a parameter of the algorithm. So I will add this in the parameters. Here, I add the epsilon. And of course, here I change the epsilon. Of course, I will modify the other algorithm in the same way with the epsilon here and here. So what is good in what I did is that I put a default value here for epsilon, which means that if somewhere I use the call find argmin golden of f, it will still work, because by default it would take epsilon equal to 10 minus 6. So that is good from the point of view of backward compatibility. But there is also a bad point. The bad point is that if I want to use this ability to vary epsilon in the big algorithm, then I will need to modify in the big algorithm. So here, not only I will take the sub-algorithm in arguments, but also the value of the epsilon. So I need to modify the signature of my big algorithm. And here also I need to modify the code of my big algorithm. The second problem is if I want to enrich the output. So, okay, when you find the zero of the function, there is a main result which is the value of the zero. But maybe you want something else. For example, the number of iterations that you have used, for example, for diagnosis purpose or whatever. So, if you want to do that with this architecture, you will, instead of returning just the number, you will return a tuple with the number and the number of iterations. And once again, you have changed the signature of your function, which means that everything that calls find zero dichotomy of f and expects to receive a number will have a problem because it will receive a tuple. For example, in my big algorithm, okay, so, sorry, I just did the same with the other sub-algorithm. So, for example, in the big algorithm, instead of doing z is equal to find point of something, you will need to modify the call so that it takes z, comma, something that I don't care about, is equal to find point of something. And of course, if you have many big algorithms that use the sub-algorithm, at all the places you will need to do the modification. So, of course, this is totally out of the question to do something like this. Now, another kind of problem. Imagine that you want to define new auxiliary algorithms that don't use the same parameters. For example, here I have a new way to take a function and to output a number. It's simply to find the zero of an affine function. Okay, so it's the dedicated algorithm for the affine functions, which is of course more efficient than a dichotomy if you know that your input is affine. Okay, so you just take f in input and you output the value of the zero. It's supposed to be a non-constant affine function. So here, just an example of application. But if you want to use this sub-algorithm in your big algorithm, it needs to have the same signatures as the others. So you will need to add a second argument with a fake epsilon that doesn't serve any purpose. And you will also need to return to a tuple of values with the second tuples meaning essentially nothing. And the fourth and the last problem will be that if you want to add new functionalities, for example, let's say that when you apply a find zero or find argmin algorithm, you want a way to plot what you did, okay, in some way or the other. If you want to do that and to have a specific way to plot for each algorithm, of course, with this kind of implementation is very difficult. And you see me coming. We are going to go to a class architecture instead of a function architecture. Okay, so now the question is, okay, we are going to do classes to implement our algorithm, but how are we going to to do the architecture of these classes precisely. Okay, so here's our first attempt. For example, so I have a family of sub-algorithms whose job is to take a function as input and to output a number. Okay, so find dichotomy or find argmin or etc. So I will define a parent class find point, and what an object of this class able to do is able to run, because it's an algorithm, and it takes a function is input and return some kind of special point of the function. It can be the 0, it can be the argmin, and so on. Of course, for the parent class, this method is not implemented for the moment. Okay, and for example, for the find 0 dichotomy, so for my run, I need to take only f, because it needs to have the same signature. Oh, sorry. It needs to have the same signature as the parent class. So the f is the input in the run, it outputs the z, and the epsilon is in the init. So in fact, when I create my object find dichotomy, I define its parameters, okay? And when I use the run, I give the argument that I want to apply to. So there's a distinction between the parameters of the algorithm and the variables, the arguments, okay? So that's our first attempt. Okay, so now in the big algorithm, right?
There is a run method for find point, the parent class.
Yeah.
And the run method for this one, so how does it work?
This one?
Yes.
In fact, this is an abstract class. So if you try to run this, it will just raise an error and say, okay, this is not implemented.
Yes, so, okay. So it replaces, I mean, there is no problem if you take the same name for a method in a subclass, it will basically erase this one?
Yeah, that's precisely the point. Yeah. In fact, this one is just here so that everybody that implements a subclass of this knows what the run of a find point is supposed to do. So it's just to inform the world.
If you forgot to make a run method in your subclass, it will raise an error.
Exactly. And if you have a reasonable IDE where you work, in fact, it will tell you, oh, this is strange because in your subclass you have not implemented this method. Are you sure that's what you want to do? Okay, if you use PyCharm, for example, and you don't implement run in the subclass, it will say, oh, you forgot something.
That's because you are using raise not implemented. So not implemented error is
yeah. Okay, so now in my big algorithm, okay, so now my sub-algorithm is a kind of parameter of my big algorithm. Okay, you can imagine variants of the big algorithm that use a different sub-algorithm. Okay, so when I define an object of the class big algo, I will take as a parameter the kind of find point algorithm that I want to use. And now when I run the big algorithm, I take the arguments, which are the function and the amount of translation, okay? And I just do, okay, self find point. So this is the find point object that I put in the init. I use the run method of this find point object to find the 0 or the argmin or whatever. And then I add the amount of translation. Okay, so this is just an example. And then you can do in one line, for example. So big algo of find point equal find 0 dichotomy of epsilon 10 minus 6. Okay, so these launch the init of the find 0 dichotomy class. So this creates an object of the class find 0 dichotomy. This object is stored in the find point of the big algo, and then we apply the run method of the big algo to f and to the amount of translation. Okay, so now we are going to try to enrich the output and see if we still have problems or not. Okay, so let's imagine that we want sometimes to access the number of iterations, for example, in the dichotomy. The problem is that we don't want to break the API of the class. So we still want that the run method outputs z and nothing else. We don't want that it outputs a tuple. Otherwise, it breaks the API, and the big algo needs to change the code. So what we are going to do is that we are going to define a computed variable. And here I will use the convention that is used in the package Scikit-learn, which is to use a trailing underscore at the end of the name of the variable. Okay? So I will define a self number of iteration underscore, and at the beginning it's simply none because I not computed it for the moment. And during the run, I will compute this number of iterations. So the meaning of the trailing underscore in Scikit-learn is to say, okay, the value of this variable makes sense only once you have done the run. Okay? Before the run, it just makes no sense. Okay, and now I can do something like, okay, find point is equal to find zero dichotomy with some epsilon. So this defines my algorithm with its parameter. Then I'm going to run the algorithm, and I can store the value in z, for example. And then if I ask my object find point to tell me its a number of iterations, it will give the answer. So that's nice, but that's not perfect because you cannot do this in one line. It's very sad not to be able to do things in one line. But seriously, it's not only a cosmetic thing. It's also if you want to combine things and things and things. If you always have circumlocutions to do it, it's really not good. Because why can't you do this in one line? Because you need first to call the run, and the run returns a number. And once you have a number, you cannot ask the number what is the number of iterations. Z doesn't know about the number of iterations. So in fact, what you need to have is an access not to Z, but to the object itself. So what we are going to do is that now we are going to change the API one last time. We are going to say, okay, the run will not output Z, but it will output the object itself. And since you output the object itself, you can ask anything you want to the object because the object still knows everything about itself. And also, since we do that, we also need to make Z be a computed variable because that's the new way to access Z, is to ask the object, what is your value of Z underscore? So, in practice, in a subclass, so first we need to call the init of the superclass. Why? In fact, before I didn't have any init for the parent class. Now I have one because the init is in charge of initializing the variable z underscore. So since I'm polite and I want to declare my variables, I will call the init of the parent class to declare that z underscore exists. And also I declare that number of iterations exists and is a computed variable. Okay? And now instead of returning z, I will just store z in z underscore, and I will return myself. And once I have returned myself, you can ask me anything you want. So now the new syntax is like this: find zero dichotomy of parameter. So this calls the init and creates the find zero dichotomy object. Then you apply the method run to the argument f. So this outputs the object itself, and you can ask the object its value of z underscore. And the same for the number of iterations. Okay, we modified the big algorithm exactly in the same way. So now the translated point is not the output value of the run, but it's simply a computed variable, and you return self.
François,
yeah.
It is the way it's implemented in Scikit-learn?
Yes. Yes. Except that in Scikit-learn, usually the method is not called run, it's called fit. Because generally, okay, you have something, for example, you want to do a linear fit of your data, and the method is called fit. And so you just so you have some parameters of the algorithm, because you can be some variants of the algorithm, and the method fit you just take as input the data, and you return self.
So you always return self?
In Scikit-learn, yes. Yes. And this way you can ask the object anything you want.
Including piping it.
Sorry?
Including piping this object inside other treatment.
Yeah.
That's also one of the key features of this, is because if you return the object of the algorithm, it can be used as a next step, because usually when you have a pipeline in Scikit-learn, you have several steps. You treat your data, you fit it, you apply a certain classification, you apply something else, so you have a complete pipeline. And so you don't work on all the steps of the pipeline in one run. You usually have different steps, and the output of a step is the input of the next step.
Exactly. In fact, it's a way to be able to compose functions, in fact. So similar to functional programmation. Okay, so our third problem was to implement other sub-algorithms with different parameters. So we are going to check that now we don't have problems with this kind of particular case. So now I will implement my find zero find algorithm. I just define my function run, taking f as input, storing the z underscore, and returning self. And now it works perfectly as expected. So for example, I define my object find zero find with no parameter, because there's no parameter for this one. I run it and ask z underscore, it works. And also if I want to use it as a parameter for the big algo, it works also, because the big algo just wants find zero object as an input, something that is able to take an f and return itself. So it's okay, it works in the big algo. So now I have an API that I don't need to modify every time I want to change something. Okay, and the fourth problem was to add new functionalities. For example, a plot method. So imagine that I want to add a plot method that, for example, plots the f itself, so the argument, and also mark the location of the z, for example. The only problem is that for now, inside run I know f, but outside the run I don't know f anymore. So I need to store f somewhere. So now I will add another variable with underscore. It will be f. So when I have an input, I store it just in case I need it later. Okay. So just have a modification of specification for the run. I declare f here, and here I can use f if I need it. Okay, and basically it works. And what is interesting, of course, is that here, for example, it's just defined in the mother class, and I don't need to define it in the subclasses. Okay, so this I have put here only for reference, because of course the notebook is available after the talk. So if you want to have the full version of everything in Scikit-learn style, it's here in this fifth subsection. Okay, so now I will propose a variant of this architecture with two little modifications, and we can discuss afterwards if you find it good or not. So, for the moment, what do? We do, okay, I define the find zero algorithm by calling the class, for example, find zero dichotomy with some parameter. Then I can do find zero, run some increasing function, and then I will ask the value of the underscore or the value of number of iterations or underscore. But that's a bit awkward because find zero is an algorithm, so it's something like a function, something that takes an input and is able to compute something. So instead of doing find zero dot run, you would like to do simply find zero parenthesis something, like a function. So that is very simple to achieve. Instead of calling your method run, you name it call. Because call is a special method in Python, and it's the method that is used when you put some parentheses after the object. Okay? So in Python, a function is simply something that has a call method, essentially. So yeah, nothing else, just replace run by call. So in practice, now instead of doing find zero dot run, you do once you have defined your find zero object, you do find zero parenthesis of something, and it will just use the function call. And as a one-liner, instead of having find zero dichotomy epsilon nanana dot run nanana dot the underscore, you have simply the first parenthesis. So here it's a class. So when you do a parenthesis, it will call the init. So it will create the object. Now this object is created. There's some parentheses. So Python looks whether there is a call function or not. There is one. So it will use the call function here and return C. Okay. So now it's a bit of coquetry. For the moment, what we do when we do a one-liner is we use two pairs of parentheses. Essentially, the first pair of parentheses is for the parameters, and the second one is for the arguments of the algorithm. So that's not, and also, for example, if you don't use parameters, you write things like this, which is not very, very nice. And it will be more convenient to do everything in the same pair of parentheses when you want to do it directly. So what you can do for this is to create an optional call at initialization. So what you will do is that in the init, you will add the option of enter directly some of the arguments. Okay, so here the argument is f, so I add an optional argument f in the init. Okay, by default it is none. So if f is none, nothing will be done. So it's like before. And if f is not known, so explicitly entered by the user, it will directly the object will directly call itself. Okay. So this is the object itself. There are some parentheses, so it will use its own function call. It's clear? So how does it work in practice? So here we have added the optional call here. So I prefer to put the argument first because especially when you don't want to precise the epsilon, you can enter f without keywords. Okay, so you can enter it directly. And here you will call the init of the parent class. And it is the init of the parent class which is in charge of using the call at initialization. So now in this new architecture, it's important that the call to the init of the parent class is done at the end of the initialization. Because if you don't do it at the end, for example, the self epsilon is not defined. And you need that self epsilon is defined to run your algorithm. And so now things like this work. So find zero dichotomy of f and epsilon. So it does this, then it does the super init with f. Since f is not known, it's going to call itself, and then it will run this method. So this is a new possibility, but we still have the same possibility as before, so we can use the old syntax, which is first to define the object with its parameters, and then and only then to call the object. That still works. Just we have just added something and we have not subtracted anything. This old way of doing is still very practical, and we want to keep it because sometimes you have a very long list of parameters here, and you will use your algorithm, your tuned algorithm, several times. So you want to be able to say, okay, I define my algorithm, I set up the parameters, and then I'm going to use this algorithm several times. And the second reason is also when you want to use this as a parameter for your big algorithm. Of course, in that case, you just want to define your algorithm with its parameters and not call it right now with a particular function. Okay, so like before, this is just as a reference so that you can have it later if you want. Okay.
Intermezzo.
Intermezzo.
Yeah. Battery change.
Battery change. Ah, okay. C'est tout bon? Okay. So, just a little intermezzo about properties. So if you already know properties, maybe you will not learn much, but I just want the talk to be self-contained. So we're going to take temporarily another example. Say that you want to implement a class representing equilateral triangle that are defined by the length of one side. And they are able to compute a lot of things about themselves. They can compute their perimeter, their area, and so on. Okay? So one way to do this is to say, okay, when I initialize an equilateral triangle, I will take as input the length of the side. And since I want to be able to access its perimeter, I will compute it right now and say, okay, it's 3 times x. Okay? Of course, here it's a very cheap computation, but imagine that you have something very costly computation. Okay? The problem is that each time that, you will create an equilateral triangle, you will do this computation at the initialization, and even if it's an occasion where you don't need the perimeter, this costly computation will be done. So you don't want to do that. So a first solution would be to create a method, perimeter, that computes it. So, okay, you don't compute the perimeter here. You define a method called perimeter, and you return 3 times the value of x. The problem is that if you, there are in fact 2 problems. There is first a small annoyance, that is now you code the perimeter with parentheses because it's not an attribute of the object, but now it's a method. And the second problem, which is a more serious problem, is that each time you will ask for the perimeter, it will be computed. So if it's costly, it's a very, very big problem. So the first annoyance is quite easy to avoid. It will be to add this magic decorator here. So just add this arrowbars property. And the job of this decorator is essentially to transform a function without argument into an attribute. So something that you usually call with parentheses nothing, it will be just without parentheses. So this is okay. Now we can code the perimeter without parentheses, but we still have the big problem, which is to compute it every time. So for people that are used to other programming language, by using property here, we essentially say that this method is the getter for an attribute called perimeter. Okay, so a first solution for this problem will be to cache the property, let's say manually, because I will show you an automatic method afterwards. Okay, so to do this, what you are going to do is at the initialization of your object, you will define a hidden variable called underscore perimeter. Okay, so in Python, the leading underscore is a convention to say, okay, this is a private variable. It's not really private because if you really want, you can access it. But I strongly advise you against accessing it because it's not part of the API, so I don't give you any guarantee about the way it works. Okay, so it's kind of lacks hidden private variable. Okay, so I defined it with the initial value known, which morally means in that case not computed yet. And when I run the perimeter method, I'm going to check if it is known. If it is known, I will compute it and store it in the hidden variable. And anyway, whether I have just computed it or not, I will return the value of this hidden variable. Yes?
Since it is a computed variable, why is there no...
Excellent question. Simply because here the value of this property always makes sense. In the sense that as soon as you have initialized the object, you can ask the perimeter, it makes sense, it has a value, okay? The trailing underscore, the meaning exactly is not that it's a computed variable, it's that it only makes sense after a run of the algorithm. Okay, so now wonderful, when I call the perimeter, it computes the perimeter and I have the value. And if I call it a second time, now the value is not known, so it will just return the perimeter. So it works. But now I have a new problem. Let's assume that during the life of a triangle, its size can change. Okay, so you can change the value of x. If you do that, okay, so you define an equilateral triangle of size 42, you compute the perimeter, it's 126, and you modify the value of x to be 51, and of course, since the perimeter is not known, it will not be computed again, and it keeps the old value, which is not correct anymore. So, there are essentially two solutions. First solution is to say, okay, x is not allowed to change. Okay, and just avoid the problem. And in fact, this is a serious solution in many cases. Sometimes you want your object not to be mutable, and you just want x to change. And the other solution is just to detect when x changes, and when x changes, you will just erase the cache. Okay? So now we are going to define a method whose job is to initialize the cache. So here it will be to put the value of underscore perimeter to none. And this method will be used in two locations. First, at the initialization of the object, because I am polite and I like to declare my variable at the initialization of my object. And the second circumstance will be when you change x. So if you don't know much about properties in Python, if you want to have a property that is called x, for example, when you use the decorator at property, it defines the getter of x. So what happens when you want to access the value of x. And the decorator at x.setter will define the setter. So what happens when somebody tries to modify the value of x, okay? So when someone tries to modify the value of x, you will do first, I initialize the cache, and then I store this new value of x in my hidden variable underscore x. Okay, so now it works as expected. When I define my triangle, okay, the parameter is computed. Then I ask the parameter a second time, it is not computed. I change the value of x and I ask the perimeter again, it's computed and has the good value. So this works perfectly fine. The only problem is that if you do that very often, it's a bit heavy to handle. And for example, let's say that you want to add a method called area. What will be the cost in code to add a new method? So you need to define this property with this if self is none, blah, 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 return self area. And by the way, you also need to put something in the initialization of the cache. So it's not much, but just don't forget that the only significant thing in this code is just that. So it's a bit, I think it's a bit expensive just to do a one-liner. No, the other way around. Okay. Okay, so for that I have defined, more exactly, I have stolen some code called arrobas cache property. So this is essentially something adapted from something that I find on Stack Overflow. Okay, so you can just copy and paste it. You don't need exactly to know how it works. If you're interested, you can have a look later. And I have also defined a mixin that is able to delete the cache of an object. I will explain all this after. Okay. Just about what a mixin is. So a mixin is a class, okay, that is intended to be used for inheritance, okay, and that just gives a small feature to its subclasses, okay? So it's not specially meant to be the parent class of an object, but usually just something, for example, that adds a small practical method or small thing, okay? So for example, if you, in this delete cache mixin, if you inherit from this class, you will just have this feature, a small method that does something, okay? And about mixins in general, the most common syntax is like this. When you define the child class, you have its main parent class. So it's the main class whom you want to derive from. And you have some small functionalities added with a mixin class, another mixin class, and so on, just to add some small functionalities. Okay, so I will show you how it works in this particular case. So I define my equilateral triangle as inheriting from delete cache mixin, which means that my equilateral triangle will have a method called delete cache. Okay, just means that. And now when I want to define the perimeter, instead of doing arrobas property, I will use my custom defined arrobas cache property. Okay, so you don't want exactly to know what cache property does, but it does what you want it to do. So, and the way you write it is simply like you would write the method, return 3 times self x, and the cache property magic, what it's going to do is that if it's not done yet, I will do it. If it's not done, I will not do it, and just take the cache value. And when you want to delete the cache, then you will do self.delete cache, which is calling this nice feature that is added by the mixin. Okay? So what you don't need to do now is you don't need to declare a variable called underscore perimeter, for example. And here you don't need to do a distinction whether this is already computed or not computed. Just need to do, okay, return the result and don't care about what happens.
It's inheriting from delete cache mixin because you are using the delete cache.
Yeah.
But the arrobas cache property, it has nothing to do with the delete cache.
No, it just define somewhere else.
And why do you treat them differently?
In fact, essentially, a decorator is something that needs to be able to take something as an argument. Okay, so it can be either, generally it's a function, and in that particular case it's a class with its init, but it's essentially the same. And so you just need, let's say, a function cache property to be defined somewhere. So either at the beginning of your code you have the definition of cache property, or you have from my auxiliary file import cache property. So now to implement a cache property, in fact you have three lines of code, the decorator, the def, and the return. The rest is just documentation. And the second thing that is very convenient is that when you implement a cache property, everything is in the same place. Because before you have to modify something in the initialization. And when the code of the class gets longer, it's very convenient just to be able to write it in one block of code. And it works. Okay. I will not dwell on this section. I have tried all other ways to do the same thing. So I have two other ways to do the same thing that don't work. So if you're interested why, you can ask me later. Okay. So now we are going to use these cache properties in our architecture.
So this is not implemented in Scikit-learn?
No.
So how do they manage this kind of problem?
I don't know. What I suspect is that when you launch the fet, the fit method, it performs the algorithm, okay? And so it computes what needs to be computed, and maybe it does a bit of not necessary computation, but I'm not sure. It should be checked. And what we will do here is precisely to use this property to delay computation as much as possible, okay? And especially we'll try not to compute what is not necessary to compute, okay? Just for the example, I have added another property which is z-square, just to have something with an intermediate computation. So this is like before, and this is different now. In fact, when there is the call, I don't do the algorithm at all. I just store the input and do nothing, and wait for people to ask me what they want to know. Okay? So I just store the value of f. I delete the cache because, of course, if I have used the algorithm before with another function f, all my computed variables are not valid anymore. So I delete the cache to forget what I could have done before, and I return self so that people can continue to do something with me. Now z will be a cache property. So for the moment it's not implemented, and z-square, for example, will be also a cache property. And I don't know what is under. Ah yes, I have still my plot method. Okay, so now when I want to implement a particular algorithm, I just have to say, okay, how do I compute z? Okay, so now z is simply this. This is essentially a one-liner to code. And for example, if I use this, so here it's the optional call at initialization, and I can ask z-square because the computation of z-square is defined in the parent class. So yes, so z-square will try to put z underscore to the square, but since z underscore is not computed, it will call the computation of z-score. The computation of z-score will be computed, it will be cached, and so on. So after that, if I ask for z underscore, of course it will not be computed because it is already computed and stored. Okay, once again, this is just a reference to have the final version of the architecture. Okay, I will not dwell on this. Okay, so in conclusion, I will just show you. So on a toy example, I find it a bit difficult sometimes to see why it is interesting to do things like this, because yeah, it's a toy example and it's difficult to know what is at stake. So I will show you a simplified real example. So it's about a voting package that I am currently working on with some colleagues from Dauphine and Grenoble. And I will just take the example of plurality voting. So the principle is that people vote for one candidate. So each voter votes for one candidate. And then you simply have a look at how many votes each candidate gets. And the candidates with most votes is going to win. Okay, so what we would like to have is something like, okay, I define my election like this. Okay, so that I have 1 people voting for A, 3 people voting for B, and 2 people voting for C, for example. And once I have applied this election, I want to be able to access the scores, for example. So 1 votes for A, 3 for B, and 2 for C. I want to be able to access the winner, which will be B in that case. And I would also like to be able to access the strict order. For example, here B is first, and C is second, and A is third in score. So what's it going to look like? So I define my algorithm. Here it's the optional arguments at initialization. So you can call with some specific ballots if you want at initialization. This is a parameter, so it's just to know if you, when 2 candidates are tied, whether you give an advantage to the first in alphabetical order or to the last in alphabetical order. Okay, so just you sort ascending or descending. So you store the value of the parameter. And if you have some arguments, then you launch the object itself. Okay? When you launch the object itself, simply you delete the cache and you store the input. And then everything is implemented as a one-liner as a cache property. So for example, the scores, just essentially you count the ballot. The best score, you take the max of self-score on the score. So which means that if scores is already computed, just take its value. If it's not computed, it will automatically compute it, and so on. And then the co-winners, the winners, the order, and so on. And essentially it works. So I really want to insist, I find that this implementation is very, very convenient to code and to use. So here, for example, I have some dependencies on my computed results. Anyway, I need to compute the scores. The scores are used to compute the best score. The best score is used to compute the list of co-winners, that are the people that have the best, all the people that have the best score. And the list of co-winners is used to compute the winner where you use the tie-breaking rule. By the way, the scores can also be used to compute an order. So it's a weak order with some ties possible. And this weak order is used to compute the strict order, where the ties will be broken according to the tie-breaking rule. So for example, if you ask the winner, it will need to compute the co-winner, the best score, and the score. But of course, the strict order will not need to be computed. But in fact, you don't have to care about that. And that's all. Thank you very much. Questions, remarks?
Doesn't this mean that Python should evolve? Because it looks like you have these decorators and it looks like a trick.
Yeah. I don't know. In fact, so there is a PyPy package called cache properties. So the need has been identified by some people, but as far as I know, this package cache properties doesn't have the functionality to delete the whole cache of an object. So it exists, but partially, at my knowledge.
So this is not implemented in Scikit-learn in the sense that if you want to do, I don't know, clustering and you are asking directly for the cluster, it will fail. You need first to do a fit and then...
Yes. Yes.
But if you use this, you could directly get...
Yes.
Without putting the fit.
Yes. In fact, you do the fits because you have the parenthesis. You have the parenthesis and you give your arguments.
If you don't need to recalculate properties like often, is there any performance trade-off between this and just like a simpler architecture?
I don't know, sincerely. I guess not much, especially if your computation are a bit costly. I think it's neglectable. But
the properties cost nothing in Python, and just assigning object to this kind of value doesn't cost much. But one good thing that this architecture brings is that all the code you've seen in this presentation is examples that work on a single machine. Like all the data, all the object is stored in a single memory instance on a single Python interpreter. If you can, inside your object, deal with the fact that some of your data will be remote on clusters that are involved like weeks of calculation, this kind of ease this kind of syntactic sugar will be very appreciable because it will directly map to cache management on the background. Because here it's just assigning object to assigning attribute to an object inside the same memory of the process. So it could ease up computation on a single machine, but it could be avoided for simpler architecture. In case you have heavyweight computation with very large data set, these kind of tricks are just mandatory, otherwise you will not be able to scale to massive amount of data. And as a matter of fact, I would one of the things that you said earlier was if you can go for immutable data. I can't stress it enough. If you can, do. In case you cannot, these kind of things works fine. But if you are working with some programming languages that are immutable, or you want to ease up a lot your computation and you are ready to pay the price to have a simpler code, pay the price. But sometimes you cannot have this luxury.
But I think that already these simple examples in the talk show two quite different cases. The first one is the triangle, which is really an object with some properties, and maybe it's a good idea to make it immutable anyway. If you need another triangle, just define another triangle. But the second example is having an algorithm object, which is the main example. And in this example, for me, it makes sense to have it mutable because you can, many times you will want to define your parameterized algorithm with some fine-tuned parameter and then use it several times on different arguments.
Yeah.
So in that case, you want it to be mutable and to be able to, for example, in my example, to change the value of f because you want to apply the same algorithm to different arguments.
Yes.
Nathan, you have already tried a bit to implement things like this?
I'm still at the Scikit-learn step.
Okay.
So are you ready to check all our code?
No. No more questions, remarks?
Thank you again.
Thank you.
Merci.